So-called Mercury dimes were minted between the years 1916 and 1945, and they contain silver, which is probably why you rarely see them in circulation. Roosevelt dimes also contain silver, although only the ones that were minted before 1965. We're going to determine the amount of silver in a Mercury dime through a gravimetric analysis. Alloys are mixtures of metals or a mixture of a metal and a nonmetal. The alloys themselves generally have desirable properties that the pure elements do not have. If the atoms of the elements being mixed with the pure material are relatively close in size to the atoms of the pure element, the alloy formed is the substitutional type of alloy. In this type of alloy, another atom of a different element simply replaces the atom of the native element. If the atoms being mixed with the pure element are much smaller in size than the native atoms, they will occupy the spaces between the native atoms. In other words, the interstitial spaces. These types of alloys are understandably called interstitial alloys. Most coins in the US are alloys of some type. The so-called Mercury dimes minted in the years between 1916 and 1945 are alloyed with silver and copper, 90% silver and 10% copper by mass. We're going to confirm these percentages through a gravimetric analysis. The first step is to take a small measured fragment of the coin and dissolve it in 10 milliliters of 6 molar nitric acid. You will notice that a brown gas, nitrogen dioxide, is produced, and over time the solution will turn a bluish green due to the presence of dissolved copper ions in the solution. The resulting mixture will contain dissolved silver and copper ions, among other ions. The reaction below shows the production of the silver ions as well as the toxic nitrogen dioxide gas, which explains why we will be doing this procedure in the hood. The next step is to precipitate the silver ions by adding a solution of sodium chloride. Silver chloride is an insoluble compound, and so the addition of sodium chloride provides a source of chloride ions, which when combined with silver ions will cause the precipitation of silver chloride. We will then collect the silver chloride by vacuum filtration, as before, dry the silver chloride overnight, and mass it the following day. And so the lab plan is as follows. We'll measure the mass of the alloy, the coin fragment, and the Gooch crucible and filter paper. We will dissolve it in 6 molar nitric acid. We will precipitate the silver ions with excess sodium chloride solution, and the precipitate will be, of course, silver chloride. We'll collect, wash, and dry the silver chloride. We'll mass it. We'll determine the mass of silver in the fragment and, of course, the percentage of silver in the coin fragment. So I have some sample data on the screen where we have a mass of a coin fragment as 0.5503 grams. We'll need to ensure that the chloride ions are in excess. In other words, to ensure that we completely precipitate the silver ions as silver chloride. So to do that, what we do is we add twice the amount of sodium chloride that we need to precipitate the silver ions. And so that calculation you see on the screen shows how that would be done. Once we precipitate the silver chloride, we'll need to mass the Gooch crucible and the silver chloride. Suppose that mass is 21.0196 grams. From there, we can calculate the mass of silver chloride, which in this case will be 0.6434 grams. We'll need to determine the percentage of silver in silver chloride, and we can do that by taking the mass of silver and dividing that by the molar mass of silver chloride By calculation, you see that is 75.27%. And so we can determine the mass of silver that's in the alloy by multiplying that percentage by the mass of the coin fragment. In this case, the mass we arrive at is 0.4843 grams. From this, we can actually calculate the percentage of silver in the alloy by taking the mass of the silver in the alloy and dividing it by the total mass of the coin fragment. In this case, we get 88% silver. The coin fragment is assumed to be 90% silver according to APMEX, which is a company that is a dealer in silver coins. Assuming that the accepted percentage of silver in the coin is 90%, we can calculate an experimental percent error, which in this case, assuming our measured value of 88%, we get a percent error of 2.2%.
Since we will be collecting the silver chloride as a precipitate by vacuum filtration, as before, we will need to obtain the mass of the Gooch crucible and filter paper. So the mass of the Gooch crucible and filter paper is 19.7641 grams. So we'll need to obtain the mass of the silver fragment. So I'll take it over to my scale. We put on the scale, zero it out. And obtain the mass. So the mass of the fragment is 0.3484 grams. The next step is to dissolve the coin fragment in 6 molar nitric acid. I'm performing this procedure in the hood, the fume hood. You may be able to see the coin fragment dissolving. This process will take some time. I will check back in a few minutes. 3 minutes have passed. You may notice that the solution is now blue-green. You may see the faint appearance of a brown gas. Let me just kind of turn this around a little bit. Maybe you can see this. Very faintly brown tinted gas above the liquid. That is the nitrogen dioxide, which is a toxic gas, which explains why we're doing this in the fume hood. The coin fragment is completely dissolved. There is no more nitrogen dioxide being evolved. At this point, I'm going to precipitate the silver as silver chloride by adding a solution of sodium chloride. I've carefully measured the amount of sodium chloride to be twice the amount that I need to precipitate the silver as silver chloride, just to ensure that I precipitate all of the silver ions. So now I precipitate the silver chloride ions. Note that the solution turns a milky white. That is the appearance of the silver chloride ions. Excuse me, the silver chloride solid. So I'm going to just let that sit a little while, and then I'm going to collect the precipitated silver chloride using vacuum filtration as before. Okay, so as before, I have my Gooch crucible and filter flask and aspirator ready. Just going to make sure the filter paper is wet to give it a good seal. Notice that it's pulling the liquid through.
and make sure that's got a good seal. Okay, now I'm going to begin filtering my silver chloride precipitate. So I have some silver chloride stuck to the sides of the beaker. I'm going to make sure I get it all by using my wash bottle and washing that into the gooch crucible. This next step I didn't show, but this time I'm going to wash the silver chloride crystals with copious amounts of distilled water, and that is to remove any remaining ions that may be present in the crucible. I don't want them to recrystallize when I dry the crystals overnight, because that will affect my results. I've quantitatively transferred the silver chloride to the gooch crucible. The liquid in my filter flask looks relatively clear. That means I didn't lose much, if any, silver chloride. So I'm going to wait for the rest of this to filter through, and then I'm going to take it off of the Walter adapter, and we're going to pop it in the oven to dry overnight. Okay, so the silver chloride crystals have been washed thoroughly, and they are ready to go in the drying oven to be dried overnight, and we will mass it the next day. Okay, so the silver chloride is ready to be massed. One small problem, I do notice that the filter paper seemed to have curled up during the drying process, but didn't appear that I lost any silver chloride, so that shouldn't be a problem. So I'm ready to mass the gooch crucible, the filter paper, and the silver chloride. And the final mass is 20.1851. At this point, you should be able to calculate the percentage of silver in the silver coin.